I'm Alex King. I'm the director of the Critical Materials Institute here in Ames, Iowa, and I'd like to welcome you. Rare earth elements with essential roles in high-efficiency motors and advanced lighting are the most prominent of the critical materials today. So how do we assure the supply chains of critical materials for clean energy technologies? The answer is innovation across the entire supply chain. Through our innovations, the Critical Materials Institute achieves three main goals. We diversify and expand production. We reduce wastes through reuse and recycling of materials. And we develop substitutes with similar properties to current critical materials.
So the Rapid Assessment Project is mainly focused on developing new alloys in a time frame that is rapidly accelerated compared to conventional methodologies. And we do this via two really primary techniques. We look at things from a thin film method, which is very conventional in rapid assessments, combinatorial material science. We do a lot of thin film sputtering where we can create large alloy libraries over large composition spreads very quickly. But thin films aren't always the most desirable way of making things when you're looking at alloys like magnetic alloys where size can have a large effect on the properties. So the other way we will make libraries is using bulk combinatorial synthesis. In that case, we use additive manufacturing equipment, in this case a lens system, laser engineering net shaping, where we can print samples, bulk samples, several millimeter dimensions. And we can print these very quickly, much faster than we could ever make using conventional processing like injection casting or melt spinning or any other way. So in this case, we now make these alloys. That's just the first step. We now need to be able to characterize these alloys and pick out some properties very quickly. So as part of our project, we have very rapid assessment equipment, rapid characterization. So one of the first steps would be taking something like micro XRF, which we have downstairs. We can quickly, on a micro scale, look at the compositions. This characterizes each individual point over about 30 microns and tells us what the composition of these alloys are. And that tells us how good of a composition spread we've covered. We do these for both the bulk and thin film alloys. We'll then take these alloys and we'll go to a different characterization equipment that could be X-ray diffraction, where we have auto samplers where we can quickly identify the phases that are present in these alloy libraries. So we have very unique equipment, only one in the world actually, where it's a auto sampling DSM. We can put several samples in and very rapidly measure all the magnetic properties. So when you add this all up, we now can identify really important properties, compositions, structures, and this helps us then to really accelerate the development of new alloys that are important or critical to the CMI.
We grow single crystals so that we can directly measure the different orientations. We have several furnaces so that we can look at different systems in parallel and this way be really fast in our search for new substitutes. The nice thing is that we can directly characterize our crystals and take a decision whether these crystals are good or not for permanent magnet applications. And we can go back to crystal growth and try to improve the material properties. We can do this circle of growth, characterization and decision very rapidly because we have all this equipment in place.
My name is Vitaly Pecharsky. I'm a distinguished professor at the Department of Material Science and Engineering, and I'm also a faculty scientist at the Ames laboratory, and I'm associated with the CMI. There are two kinds of research that I do for CMI. One is related to the project which is named Rapid Assessment Methodologies, and within this project my main job was to develop a unique piece of equipment which is a semi-adiabatic calorimeter which is capable of measuring specific heat of solids. The specific heat data, the heat capacity data, which are being measured in this calorimeter, which we already completed developing, are critically needed to provide some basic thermodynamic data for materials that are being studied within the CMI, and specifically These critical thermodynamic data will be used by modelers within the CMI to really being able to predict properties of materials related to the CMI mission. The second project that I'm involved in is actually related to developing substitutes, and one of the materials we're working with is related to red phosphorus, trying to eliminate critical rare earth materials, rare earth elements from red phosphorus. And we are taking a pretty unique approach where we prepare very uniformly doped aluminum nitride doped with manganese, which appears to be very good red phosphor, which can be excited by UV light and actually gives that very nice, very bright red light. So these basically are two projects that I'm working on within the CMI.
With our aggressive goals, our specialized research facilities and equipment, and more than 300 outstanding researchers, the Critical Materials Institute is well poised to make a big impact on the materials critical for clean energy technologies.